Let's try setting up another integral for the volume of a solid region. So I'm going to ask you to read part B. Remember, this was example 4 in your textbook. And let's look at part C together. So we want the region bounded below by a paraboloid z equals x squared plus y squared, and above by the sphere x squared plus y squared plus z squared equals 6. Okay, again, you should always try to get a rough sketch. So here's what my paraboloid kind of looks like. And what's happening is I've got it's capped off by the sphere on top. Okay, where the sphere has radius root 6. Okay, so the region of integration here, let's think about what's happening. As I take my little pieces of the volume, they're going from the paraboloid up to the sphere. Okay, so my bounds on z are the paraboloid to the sphere. My paraboloid had equation x squared plus y squared. And on the sphere, I'm going up to the top half, right? So I can go square root of 6 minus x squared minus y squared. Now, what about my region R for x and y? Well, I want to think about projecting sort of the widest region here down onto the xy plane. And so what I need to know is where this intersection is happening. Okay, so I'm projecting onto the xy plane. And I want to find where the surfaces intersect. Well, they're intersecting when their z values are equal. So I want to set the equations equal. So I have z equals x squared plus y squared. And if I plug that in up here for x squared plus y squared, I get z plus z squared equals 6. Or z squared plus z minus 6 equals 0, and that factors as z plus 3 times z minus 2. So z equals negative 3 or z equals 2. Now I look back up here at what's happening. I know that z is not negative because we're looking at the positive z values. Okay, so z equals negative 3 can't happen, so it must be that z equals 2 is when my surfaces intersect. So my surfaces intersect when x squared plus y squared equals z, which is 2. Okay, so that's going to give my region, whoops, well, that's a terrible circle. Let's try again. That's going to give my region here. It's a circle of radius 2. And so I, again, could go vertically simple or horizontally simple. Let's go vertically simple. So what are my bounds on y? Well, y goes from the bottom of the circle up to the top of the circle. The bottom of the circle has equation negative square root of 2 minus x squared. And the top of the circle has equation positive square root of 2 minus x squared. And finally, what about my bounds on x? Well, x runs from negative square root of 2 to positive square root of 2. Okay, and once I know those bounds, I can plug it into the integral. I am out of room on this slide, but I don't want to leave this slide, so I'm going to squeeze it in up here. I'll use a different color. So I need the integrals, triple integral dv, where whoops, let's not do dv. Let's actually do what our things are. So I'm going to do dz on the inside, then dy, then dx. So z ranges from x squared plus y squared to the square root of 6 minus x squared minus y squared. The bounds on y are negative square root of 2 minus x squared to positive square root of 2 minus x squared. And the bounds on x are negative root 2 to positive root 2. And that's going to give me volume. All right, let's try another example. I want to determine the volume of the region that lies behind the plane x plus y plus z equals 8 and in front of the region in the yz plane bounded by z equals 3/2 square root of y and z equals 3/4 y. Okay, so first of all, let me sketch this region in the YZ plane. So z equals 3/2 square root of y does something like this. And z equals 3/4 y. Oh, yeah, 3/4 y does this. 3/2 square root of y. And these intersect when y is 0. Oh, I'm sorry, when y is 0 over here. And when y is 4 and z is 3 here. Okay. So here's the region in the YZ plane. Now imagine that I take this in the YZ plane, and if I were to tack my x-axis on here, I'm going to sort of trace this out until it hits the plane x plus y plus z equals 8. So that's sort of the idea of what this region looks like. Now that's a very ugly drawing, so let's pick it up in Grapher just to look at it. But that's what we're thinking about. Oh no, it deleted it. All right, let's put this in real fast. So I have x plus y plus z equals 8. And z equals 3/2 square root of y. Whoops. And z equals 3/4 y. Okay, and of course they're all the same color. Let's change this one at least. All right, so the red is x, right? And so we're going to start over in the YZ plane where x is 0, right? And we're between those two cylinders. Z equals 3/2 y and z equals 3/2 square root of y and z equals 3/4 y. And we're going to look at the volume between those two cylinders from the YZ plane up until the plane x plus y plus z equals 8. All right, so in this case, it's natural to first put our bounds on x because it's easy to see that x is going from 0 here in the ZY plane to that plane x plus y plus z equals 8. Okay, so I'm going to put my bounds, on x. x goes from 0 to the plane x plus y plus z equals 8, which is 8 minus y minus z equals x. All right, and now we can focus in on the yz plane to get our bounds on x and y. And it's going to be most natural to take vertically simple region. So z is going to go from the line up to the curve. Does everyone see that? So z goes from 3/4 y to 3/2 root y. And finally y, well, we can see here, y goes from 0 to 4. All right, so the volume of this region is the integral. Let's do the triple integral. We're going to do dx, dz, dy, where x goes from 0 to 8 minus y minus z. Z goes from 3/4 y to 3/2 root y. And y runs from 0 to 4. All right, just for the sake of time, because I know your attention span is a little short when you're watching these videos, I'm just going to tell you what the answer is. I get 49/5. You should try this integration yourself and let me know if you're unable to get that. We can do a Zoom session and work it out together.